Gibson here. Today we're going to move on to the next lesson in this unit on linear and quadratic functions. Today we're going to look at transforming quadratic functions. So we already looked at transforming linear functions, and we saw that we had different types of transformations like horizontal and vertical shifts, reflection, stretch or shrink, and we're going to see that those exact same transformations apply to quadratic functions, just they look a little different. So here's our objectives for today. Recognize the different transformations of a parabola. Parabola is what we get when we graph a quadratic function, and then use the vertex form to graph a parabola. All right, so a little review here. The graph of a quadratic function is a parabola. It opens, in this example, up. There's a couple key features here of the parabola. The first is the axis of symmetry. So this is the line that divides the parabola into two equal parts. It's a vertical line. The other key feature is the vertex of a parabola. That's the point where the parabola intersects the axis of symmetry. Now, another way to think about the vertex is that if the parabola opens up, then the vertex is what we call a minimum. It's at the bottom of the parabola. If the parabola opens downward, then it occurs at a maximum or top of the parabola. Okay, so axis of symmetry and vertex, the two key features of a parabola. Now, when we transform a quadratic function, or any function for that matter, right, we want to define what is the parent function, the most simple form of the function. So the standard form for a quadratic function looks like this: y equals ax squared plus bx plus c. The parent function is just simply y equals x squared. So in order to get the parent function, here are the conditions for our coefficients, a, b, and c. A is equal to 1, and b and c are 0, which means if we multiply those by 0 or we're adding 0, they just drop out of the form, and we're left with the parent function, y equals x squared. So another way to think about it is we have no linear term, bx we refer to as the linear term, and no constant, c. Now, what does the graph of the parent function look like? Well, it opens up. It has an axis of symmetry at x equals 0. So that vertical line is right on the y-axis. And the coordinates for the vertex are at the origin, 0, 0. Now, it's helpful to have a couple more points to see what it's going to look like. So what would happen if we put in 2 for x? We're going to square it. So 2 squared is 4. Let's do the same for negative 2. So negative 2 squared gives us also positive 4. So now we can sketch in our parabola. Okay, so that's what the parent function looks like for a quadratic function, the family of quadratic functions. Y equals x squared. The key thing to remember is that the vertex is at the origin and that it opens upward. All right, so what do the different transformations actually look like? Okay, let's start with our parent function and we'll step through it. So the first is a reflection. So this is where we simply take the points that are above the x-axis and reflect them down below. So it would look something like this if it's reflected. The parabola now opens downward. How about a horizontal? We move it left or right. So we would just shift the entire parabola. So in this example on the graph, we've moved it 3 units to the left. How about vertical? Well, we just move the entire parabola up or down. So in this example, we've shifted it up 5. And then the last transformation is a stretch. Now, the way to think about this, if we grab the parabola at the top and the bottom and pulled it, stretched it like a rubber band, it's going to get narrower, right? So it would give us a narrower or skinnier parabola. A shrink is just the opposite. If we squished it down, it would kind of squish out along the sides. So we get a wider looking parabola than the parent function. Okay, so that's it. A reflection opens down, horizontal and vertical. You know what that looks like. The entire parabola moves left or right, up or down, and then stretch makes it narrower, shrink makes it wider. So let's look at some examples here, see if we can identify what transformations are being applied. So the dashed gray line is our parent function. The red line is the transform function. So let's go through this first one together. Is it reflected? Well, the answer is no, right? It still opens up. So no reflection. How about horizontal? Yes, we can see everything has moved 3 units to the left. How about vertical? No, the vertex is still on the x-axis, so no vertical. And is it a stretch or shrink? Well, we can see the transform parabola is wider, therefore we have a shrink. Okay, so that's all we're going to do in a couple of examples here is see if we can identify the transformation. Okay, let's look at the next one. I'm just going to let you hit pause and then we'll put the answers up. Okay, so reflection, yes, opens down. Horizontal, yes, we've moved it 3 to the right. Vertical, yes, up 4, right? Look at the location of the vertex. That's the key thing to look at for horizontal and vertical transformations. Shrink, yes, much narrower, right? We've done a stretch to this. All right, let's look at another one here. Go ahead and put it on pause, see if you can figure this out. Okay, reflection, yes. Graph opens downward. Horizontal, no. Vertical, no. Notice the vertex does not move. It's still at the origin. And it has the same width as the parent function, so we do not have a stretch or shrink. All right, last one here. All right, reflection, yes. Opens down. Horizontal, no. The vertex is still on the y-axis. Vertical, yes, we shifted it up 5. And stretch or shrink, we can see that it is narrower than the parent function, so that would be a stretch. Okay, now we're going to introduce what we call the vertex form of a quadratic function. And here's what it looks like. F of x, remember that's our function notation, equals a times x minus h squared. That whole expression inside the parentheses is squared plus k. So this should look familiar, right? The h and the k and the a we saw in our linear transformations. So why do we call this the vertex form? Well, it turns out that the coordinates of the vertex are the h and k values here, because that's how far we're going to move the vertex from the origin. The axis of symmetry turns out to be whatever our h value is. Now, we've got to be a little careful. Again, the standard form has subtraction in it, so we have to take into account that negative. Whether it stretches or shrinks, the criteria is the same. If a is greater than 1, it's a stretch, so 2 or -3, and we're only interested in the absolute value. And then if it's less than 1, it's a shrink. Right? So values like 1/2 or -2/3. And then if a is negative, that's going to give us a reflection. So let's look at this example. The x-coordinate of the vertex is the opposite of the h if we include the sign here. So in this example, we have x minus 4. So because the form has a negative in it, the h value is actually a positive 4. Okay. And k would be equal to 1. In this example, right, because we have plus in here, but the original form was negative, that means our h value is actually a -3. Okay, so if you're trying to get to the h value to find the coordinates of the vertex, just think the opposite of whatever the sign is in our equation. So this table, we filled this out once before for linear functions. It's going to look the same for quadratic functions, right? If a is negative, that's a reflection. If a is positive, greater than 1 rather, that's a stretch. If the absolute value is less than 1, that's a shrink. The h value, if h is greater than 0, including the sign in front of it, so we're going to think opposite here, that's going to shift it left. If it's negative, we shift it right. And then the vertical k, if it's positive, we shift it up. If it's negative, we shift it down. Okay, so again, this is a good table to have summarized in your notes Everything in the table is exactly the same that we had for linear functions. The only difference is the form of the equation, right, that gives us this family of transformed functions. So let's look at a couple examples here. See if we can identify the transformations from the equation rather than the graph. So do we have a reflection? Well, we would be looking for a negative in front of the parentheses, and there is none. So we would say none. How about horizontal? Yes, we have a -3. So we're going to think opposite of that. We're going to go 3 to the right. Vertical, k is a +2, so up 2. So where will the vertex be? Well, think about it. If we move 3 to the right and up 2, that's going to take us to a coordinate of x = 3, y = 2, where the new vertex would be. Stretch or shrink? None. A is equal to 1. If there's no a value in front, you can assume that it is 1. Let's try another one. Okay, reflection, yes, we have a negative. Horizontal, +2, so we're going to go opposite to the left. Vertical, down 5. So the vertex would be at -2, -5 if we go 2 to the left and down 5. Stretch or shrink? None, right? A is equal to 1, or -1 in this case. All right, let's try a couple more. Reflection, yes. Horizontal, +4, so 4 to the left. Vertical, 1 up. Our vertex then is going to be at -4, +1. And a stretch or shrink, we have a -1/2. So absolute value is less than 1. That's going to give us a shrink. Reflection, no. +3, not a -3. Horizontal, yes, -5, so 5 to the right. K value is -3, so down 3. Our vertex then would be 5, -3. And a stretch or shrink, we see our A value is 3, greater than 1, so that is a stretch. All right, a couple more here. Reflection, no. Horizontal, +6, so 6 to the left. Vertical, -2, so 2 down. Vertex then would be -6, -2. A stretch of 3. And the last one. Okay, reflection, yes, we have a negative. Horizontal, -3, so we're going to go the opposite, 3 to the right. There is no k value, notice, in this, so that just means k is 0, no vertical. So the vertex would be 3, 0. And then we have a -0.5, so the absolute value is less than 1. That's going to give us a shrink. All right, last thing, how would we graph using the vertex form? Right? Can we sketch the graph? So a good thing to start with is the parent function here with the vertex at the origin, and then identify, right, where the vertex is going to wind up. So notice we have a horizontal translation of +1, 1 to the right. So we can move our vertex over to 1, and our k value is -4. So we're going to move that down 4. Notice we move the axis of symmetry with our horizontal move. And then we have a 2 in here, right? So that means a stretch, but exactly what's that going to look like? A good practice is to find another point, the y-intercept. So remember, the y-intercept is where x is equal to 0. So if we plug in 0 for this, we're going to get -1 squared, right? Which is 1 times 2, and then 2 minus 4 gives us a -2. So we can put this point on here. The corresponding point would be 2 up from the vertex, but on the opposite side of the axis of symmetry. And now we can sketch in our graph. All right, one more here, same thing. I'm just going to let the slides run here. All right, so in this case, we had both a horizontal and vertical translation, and we had a shrink since A is 1/2. So we wound up with a parabola that is wider. All right, I'm going to skip past this last example here. And in summary, we now know how to recognize the different transformations of a parabola. And if we're given the vertex form, we are able to sketch the graph, apply the transformations for where the vertex will move to, and then determine the shape of the parabola. The easiest way to do that is to find the y-intercept. All right, that's it for today. You'll find the assignment posted in Google Classroom.